Today I wanted to spend just shortly about 15 minutes or so and go over an approach to thermal design using system level modeling and what's called the thermal network method. So just starting with some motivations here, it's 2018 now, and over the years electronics have been downsized over and over and over, and they still produce heat, and managing that heat is becoming a crucial factor for a bunch of reasons. The risks that can come out of that: we see products malfunction if heat issues become too bad. The lifespan of products goes down, and that's almost across the board. There's been some very big cases of user injury because of the improper thermal management. We've seen a bunch of those in the news in the last couple of years. And of course, all that news coverage leads to reputational damage. So it's a really important thing to get right. And generally, it's something that is obviously still being done. This is a field of study and of getting it out. And it's been handled generally by individual mechanical designers, electrical designers. And what's happening, though, is that verification of performance, it's often done towards later stages of design using physical devices. So if problems do arise, countermeasures have to be considered within a smaller range of design freedom, because physical production might already be underway. However, because of all the developments we've had in recent years, it's becoming more difficult to deal with post-process countermeasures. So it's becoming more and more important to find a way to do our thermal design and to perform that analysis much earlier in the design process, closer to the concept level, where we can make these changes with a lot more design freedom. So that brings me to talking to one of the two methods I want to work into a new technique today, and that's called the thermal network method. And this is a sort of a clever method that's based on substituting the arbitrary 3D geometries by an electrical circuit, which consists of thermal resistances, capacitances, and heat sources. So it's a way to model heat transfer using an analogous electrical circuit setup. So the currents will correspond to heat flow and the nodal potentials to temperatures. And the basic advantage of this thermal network method is really fast computation time. So steady state computations of really large models can be performed within only a few seconds. So therefore, it's really suitable for things like parameter studies, and it became a popular tool for supporting the industrial design because of that. But it has drawbacks, and those drawbacks are going to be the fact that it's really difficult to actually make that initial mapping onto finding the analogous circuit. So it's actually doing that creation, which is still kind of difficult. So what I'm going to show you over here, though, is the second technique, which wasn't brought about initially to solve any sorts of problems to do with thermal networks. This is a system level modeling. Our software MapleSim is heavily involved in creating system level modeling solutions for all sorts of industries. But if we talk about it today just in a thermal design standpoint, what's possible to do now is represent this thermal network method, doing that with system level modeling. And what we use is called the Modelica standard library to make this possible. And it helps you create a fairly intuitive problem that's going to represent your thermal problem still as a thermal problem, so not having to switch it to an electrical problem. And the library that we're using is going to support everything you need in terms of convection and radiation. So the 1D simulation tool is going to be great for this, but it's got drawbacks as well, in that for many people who aren't already acquainted with system level modeling, it can just be a sort of difficult methodology to take on for complicated projects. So because of that, it can be difficult as well. So what we're looking to do really is kind of combine both of those, and by doing that, you've got some of the ease of the thermal network method in terms of fast computation times, but also you're going to still be able to keep it as a thermal problem using a system level modeling tool. So that's just a setup. Really what I want to do today was just run through a quick example to give you a sense of what that might look like. So if we're looking right now at this example here, you can see on the left is sort of a 3D representation of some heat generating components inside of a case. And on the right, what we're seeing is the heat transfer path in the electronic board and the whole case enclosure. So heat's generated in part here due to the electrical power consumed, and then it's going to be transmitted to the part surface, the substrate, and the heat transfer sheet by heat conduction. And then further, that's going to flow into the case. So it's transferred by conduction inside of the case, and it's dissipated from the case surface to the surroundings by convection and radiation. And lastly, the heat of the parts in the substrate, they're transmitted to the case also by convection through the internal air inside of the case. So there's a bunch of different factors to consider and to make sure that we're actually getting into the model that we're going to set up. And this is the thermal network method representation that you're seeing here. So what you're seeing here is the red dots indicating contact points, and they represent the positions of heat capacity for calculating temperature. And then all those resistors there are helping to model the specific heat capacities moving through things. So when modeling with a system level modeling tool based on the thermal network method, the placement of heat generating parts and temperature distribution on the substrate, there can be problems. Since the thermal network representation here, it's fairly simple. When we're modeling that physical device in a system level modeling situation, we're going to need to roughly divide that substrate in the case so that we can actually get a sense of temperature distribution. And that's going to be really important because we want to make sure we've got a suitable level of fidelity to the model here. So this is where using the 1D modeling tool comes in. Because what we've done here is we've taken the same thermal network method model, but we've done it within MapleSim, and we've used components from that Modelic library. And as described above, you can see what we've broken out here as the substrate. We've divided that into 16 different components, and the case is going to be divided for each surface in order to confirm the temperature distribution. So we're adding some levels of fidelity here just to tease out the specifics of what we need. So it's a fairly detailed model compared to just simply the thermal network method shown on the last slide. And in this, it's going to be possible to represent like the rough placement of heat generating parts and fixing points between the substrate and the case, depending on where the heat generating parts are connected in that dividing substrate. So that's kind of what our setup looks like. And we'll move on to analysis. So what happened between those two slides was we had that model created in MapleSim, and then from there we just had a variety of probes for the different parameters and variables we were looking for, and then we just ran a simulation. So what you're seeing here is the transient response of what's happening with the heat generation. So you can see here that the heat generating part B, it's rising to the highest temperature at 52 degrees Celsius. So let's say if you knew one of your design requirements was to have a steady state peak, that no part was over, say, 50 degrees, you'd see a bit of a problem here. So these are things you can spot early, and then you can start to design around. We move over to the steady state analysis just to see how hot is this case going to be when we're holding it, something like that. We can see that only the lower surface of the case is actually experiencing a large temperature rise due to that heat transmission. And the case are those 6 bars on the left of what we're seeing here, this chart. And if the case material, maybe we think about some countermeasures, we want to replace some part of the case material. It's often plastic, these kinds of cases, but let's say you wanted to change that to metal or some other one with a higher rate of heat transfer. This can be expected to really help that out, and we can incorporate that idea into a model like this with the parameters we have set up. So if we're doing that analysis and we're trying to look at what some countermeasures could be employed, we ran here on this example 2 different countermeasures. And one is to change the case material, as we talked about. And the other one would be to change it from just natural air cooling to forced air cooling by a fan. So the material change is expressed and analyzed by the physical property value, and the effect of the fan is done by changing the heat transfer coefficient of the convection. So that's all we needed to change, and then we ran another simulation. It only took a minute or two. And what we're seeing here are the results. And they measure this, they succeed in suppressing the temperature of the heat-generating component to 50 degrees or lower by changing the material. So that worked, that was good. On the other hand, the forced air cooling is also effective. But then just practically, we think that forced air cooling introduces potentially a larger host of other design implications. So we'd probably be inclined to go with the first one. So sort of as we're seeing here, it can be pretty effective to validate design concepts by combining elements of the thermal network method in a 1D CAD tool like MapleSim, a 1D simulation tool. So in this example, we actually calculated the analysis of 5,000 seconds of simulation time in less than 1 minute on just a standard personal laptop. So with efficiencies like this, we can even, let's say we can even break down our 16-part substrate into 32 parts. We can add a relatively functional level of fidelity for many people's thermal analysis, but then we can make those simulation times so quick that if people are looking to run parameter sweeps to figure out just what sort of material they need or how thick of a material they need to reach their thermal design goals, these things are very possible, and they can happen so quickly using a technique like this. So these things can be really effective, but the modeling still within that 1D tool can pose some limitations. The Modelica standard library is great to use, but sometimes, like we see here, we still had to go in and manually create those 16 different sections. So we want to get a way to improve this. And Cybernet Systems and us here at MapleSoft have jointly developed what we call the heat transfer library. And you can see here the difference between using the Modelica standard library on the left and the heat transfer library on the right when modeling a substrate that would be divided into, say, 16 parts. As the heat transfer library has components that can define those divisions with parameters, it's possible to represent the heat capacity and conduction of the substrate with only one component. This is greatly going to reduce the amount of components from 27 on the left to just 8 on the right, and the connections between all of those from 63 down to 11. And then furthermore, the heat transfer library has components that define lots of different editable thermal properties, and also each component has a dimension information as a parameter. So it's really just a way to make the process of thermal design even quicker for folks who are looking to do that concept level analysis and really tweak their design in terms of the kind of countermeasures they might need. It's a really fast way to do it on just a personal computer. So I've already told you a bit about this heat transfer library. So this is a library that's for use within MapleSim, and it comes with all sorts of different components to cover common heat transfer situations, as well as custom geometries and materials. So overall, that means you're going to have the ability to implement different shapes, different sort of multi-object configurations with a much better degree of having things already set up. So you're not going to need to do those manual 16-part substrates, for example. This is just a way to keep your head within the world of heat transfer. You won't have to go into thinking about electrical circuits. You're going to be able to create something that has enough fidelity for most situations fairly quickly. And then you can run those analyses and run those optimizations. And just rounding the circle here at the end, MapleSoft, you may have heard about us for a variety of reasons. We've been around for more than 30 years with mathematics, modeling, and computation experience. And definitely in the last decade, we've branched out and created a lot of different professional features for our software to really help in the world of industrial and professional design. Over the years, we've worked with a lot of companies to help them with things that aren't so different than what we talked about today. Just helping companies spot design errors early, give them new tools to analyze how they could improve a design at a much earlier stage at that concept level. So we've worked with a lot of folks over the years. And if any of this was appealing to you, you still might be sitting there wondering about how you'd actually take this on for yourself. And while we'd certainly sell our products as products, we also have an engineering services department that was created specifically to make the ramp-up time for these kind of projects much smaller. So if you had a thermal design problem that you were interested in, or you were looking for some other use of using system-level modeling software, trying to fix a certain design flaw with a burnt-out motor or something, our engineering solutions department can help with all those sorts of things on a sort of customized basis, and then get you trained up and ready to take this stuff on yourself, so it'll always be a tool you'll have in your back pocket to make sure that your designs come out better.